autonomous intelligence. So I am implying we aren't there yet, and that is my conviction. Okay, current AI, in my opinion, is a mere shadow of previous human thought that has been expressed in terms of algorithms, that is classical AI, or in terms of large sets of sample solutions, that is deep learning. I think in order to get anything that is comparable to human intelligence or animal intelligence, we need a very profound disruption. Goal-oriented behavior in unstructured natural environments is an unsolved problem, yes. We will need it for self-driving cars, which are on the agenda of all the car companies, of course. We will need it for service robots in normal environments. And we will need it for many other applications like surveillance. Let me compare the present situation to an overheated boiler. AI gets a lot of attention, as you know. The computing power is here, as we just heard. There are armies of talent. There are billions of investment, as we also just heard. There are tremendous application fields, but the true goal of achieving human-level intelligence is evasive. What is the missing piece? What we are running now is really a set of 50-year-old conceptual concepts. Programming, the old style of doing AI, is very expensive. Deep learning is still very slow in learning. You know, if you show a new implement, like a TV remote control, to a 3-year-old child, the child gets it on first sight and knows all TV remote controls from then on. Very efficient learning. A deep learning system needs thousands of examples. And the systems that are trained that way have narrow scope. You cannot go very far from the examples that have been shown. Jeff Hinton, one of the heroes of this development, as we have heard, says things like, "I'm deeply suspicious of backpropagation. My view is throw it all away and start again. The future depends on some graduate student who is deeply suspicious of everything I have said." That's what he says. There's a roadblock, and that's one of the two questions I want to answer today. What is that roadblock? Take the human brain as a model. It takes 1 gigabyte of genetic information to create your organism, including the brain. It takes another gigabyte of information to create the environment in which an infant grows up. Very stable and simple environment. Simulating that takes a gigabyte program in virtual reality. And after 3 years, infants can represent and understand the environment, can act in it willfully, can speak, and can learn, as I said, from single examples. That's quite remarkable. So let me just talk about what representation of the environment means. When you look at the present scene here surrounding you, or at the scene in this picture, your brain creates, in a flash of a second, a very intricate description of what is going on there. It gives you the layout of the scene, the shape of the objects, the gist of the scene, like a table set for breakfast, or rather for a photographer here. You are offered by your brain lots of affordances as to what to do. Like if you are hungry, you take a croissant and you butter it with a knife and butter, or you could sit down in the chair and so on. That is created by your brain. That is what representation means. And that is what children have in simple form when they are 3. So again, back to the human brain as a model and the information. It takes gigabytes to make it, but in order to describe the wiring pattern of your brain, it takes a petabyte. That is 1,000,000 times more. Think about it. This is a very deep message here. This is the other question. Where does this information come from? It's It's not evolution. Evolution goes through a very thin channel, 1 gigabyte, or probably much less for the brain. Where does this information come from? Now, let me, as a kind of application case, talk about a key process, understanding objects or situations. How do you understand an object or a situation? Look at this picture here. In order to understand it, you, as cognitive science tells you, you relate it to a schema on the right side. A schema has a number of nodes that refer to parts of the object, and has a number of relations or links inside it, which elucidate, which represent the relative orientation, the relative position of the parts in the object. And the schema is applied by a mapping to the actual object, mapping represented by these arrows here. That is what we call a schema, a very old idea. Some people refer back to Immanuel Kant as the first who talked about it. The Gestalt psychology talked about it. Now, in order to represent an object, you have an entanglement of schemas. Not only the functional schema I just spoke about, but you also represent color, material, make. You are aware of the position and pose. And the child who first sees the tricycle knows exactly how to move in order to get onto it. So the child relates to it by way of a body schema. And you have hierarchies of schemas. You know, these object parts are like the wheel. The wheels are represented and recognize themselves by schemas. There's a wheel schema which speaks of a hub of spokes and a rim and matches it to the parts. So you have full hierarchy of features, parts, the whole object. You see it as a vehicle, or the child sees it as a toy, and it reacts to it immediately. I absolutely must have this toy. That's a behavioral schema. Okay, comprehension of object or situations means relating them to schemas. Now, schemas have a long history, as I said. The Gestalt psychology, Jean Piaget, who spoke of the body schema, the good old-fashioned AI, Marvin Minsky, Roger Schenck, and then Weismann, they spoke of frame scripts or scene schemas. They didn't succeed in realizing this in the machine. One may ask why that was. Number one, they didn't have the processing power, and they didn't have a data structure to represent it. The relationship between a schema and its instance is one of homeomorphy. Homeomorphy talks of mappings that connect elements of the same type, elements of similar type, under preservation of links. That is what schema application is, a very general process that needs to be modeled. Now, autonomous behavior can be understood as the application of very abstract schemas defining behavioral patterns with which the animal is born to actual situations. That is how you can interpret ethology. Now, I would like to talk about the implementation issue. In my view, the implementation in neural networks that is discussed these days is the actual roadblock to autonomous intelligence. Let me argue that direction. The neural code, a claim that we need, that we don't have yet, is a data structure that can, number one, express all cognitive content. If you just look inwards, the representation of this scene, think of a data structure that is up to the job of representing this complex thing. And it comes with a very powerful structural prejudice that lets it fall into organized patterns. That is going to be the answer to the other question. Now, to make clear what I mean by the neural code or by the data structure, let me talk about the current versions. Classical AI, OFI, talks of bits. the most general thing you can think about. It has unlimited power to express whatever the imagination of the programmer has in mind, but it has no structural prejudice whatsoever. So search space for AI was a big problem. Artificial neural nets, on the other, as we know them today, on the other hand, have very limited expressive power. I'm sorry, I will probably not get this point across to you. I've had many discussions with my colleagues about this. They all imagine neural networks can express everything, but if you practically work with them to do something like representing scenes, you see that it is a very limited data structure, and it has a weak or no structural prejudice. The structural prejudice in our neural networks of today is the layout structure, feed-forward, is put in by the engineer, is not implicit in the material. So let me talk. So my judgment is bits are too wide a framework, neurons are much too narrow a framework. There must be something in between that is realized in your brain that we haven't described yet. So let me talk about neural face recognition that Schuon referred to earlier. That's the way I did it at the time. The idea was that the face comes in to primary visual cortex as a two-dimensional array of local texture elements. We know that, that's an experimental fact. I take it seriously that there are lots of horizontal connections in primary visual cortex that connect those activated neurons as a two-dimensional array, as a two-dimensional network. In order to recognize it, I said then, and I still believe that's true today, you need a model of this in another part of the brain, the intertemporal cortex, the fusiform complex, a model of it that is homeomorphic to the incoming picture, has the same, with some accuracy, same structural elements, same feature elements, in the same arrangement, same type of network, a two-dimensional array. And in order to discover this homeomorphy, you need connections that have a tendency to connect neighboring points here, linked points here, to link points there. That's the machinery. Think about this decision process. Oh, it is Obama. This is not a one neuron process that says an Obama neuron. This is a swarm process. It's a collective process of thousands and many thousands of neurons and connections discovering that they are in their preferred environment. That is created on the basis of a natural tendency of the individual elements to fall into patterns with their neighbors. So both instant, schema, and mapping between them are represented in neural terms. You don't have to think in terms of individual neurons, but in terms of structured pieces of network that fall into place. That's the big step that I'm advocating here. So a long time ago, I have proposed the dynamic link architecture as neural code. It has as variables nodes, individual neurons, as everybody has, and links. And the links form structured nets. I will come back to that, what the structure is. Those nets, or net fragments, activate and deactivate on the fast time scale. That's the jump you have to make, and that my neuroscience colleagues don't accept at the present time. And there must be a very powerful structural prejudice of the network to fall into certain connection patterns, and the mechanism is very well known to biologists, is network self-organization. Just a word about that. A network, a set of neurons that fires stochastically creates a signal arrangement on the right-hand side, a sequence of events, on which you can observe correlations, which act by the well-known process of synaptic plasticity, heavy plasticity, back on the structure of the network, and this loop runs long enough to reach an attractor state. And the big question here, the important question is, what are those attractor states? That is the structural prejudice of this neural code. Of course, the environment plays a role, I didn't forget that. Let me just talk about the interactions between the links that are important. An individual link can only grow if there are alternate pathways, like this here, lots of them, at least 10 of them or so, that help it to create a correlation. So this is the interaction between links. Certain link arrangements like this here stick together and impose their structure. And there is, of course, a constraint, a limiting that growth, which has to do with competition of incoming links to one euro. Sparsity is the other constraint. Now this is the mechanism that creates the petabyte of connectivity in the brain. Network self-organization. It has been extremely well studied in ontogenesis. I will relate to that briefly, but it is neglected at the present time. When we talk about a range of architectures that you are familiar with, which illustrates this picture, that the interactions between elements can create large-scale structure, like the interaction of soap molecules leads them to form membranes, and the membranes fall into patterns like bubbles and minimal surfaces. You know, Plateau's problem, these surfaces are minimal under the constraints. So I would like to install in your brain the idea that maybe the sphere is there first, and instead of the sphere as an idea, as a structure, as a mathematical structure, the bubble, the spherical shape, and it's just waiting for molecules to come in order to realize itself. That's the idea I would like to put into your mind, that mind structures are there, pre-existing in some mathematical sense, and they are waiting for neurons to be realized. There are other examples, like if you mix oil, soap, and water, you get complex structures which can serve as a model for what goes on in the living cell. Or snow crystals, of course, a highly structured universe, very rich universe, all made up by the interactions of water molecules. The whole universe is this restricted set of patterns, all hexagonal arrangement, for instance, which is made by the elements. So architectures like these are made in two stages. First, the laws of interaction of the elements, and then the optimal patterns that are preferred by these interactions. I will have to go through this very briefly. I said this process of network self-organization has been well studied in ontogenesis, in the growth of the embryo. And the study case 40 years, 30 years ago, in which I took part, was the growth of connection between the retina and the eyes and central structures, usually the optic tectum in frogs and fish. Originally, when the fibers arrive there, they are completely disorganized, and at the end, they form a mapping of pictures to pictures, neighbors to neighbors. I will go very briefly through a simulation in a model case where there is it's a very old work I did with David Whitshore, when you have a one-dimensional retina of 18 cells and a one-dimensional tectum. You start out with a random connectivity. You apply the rules I already introduced, positive interaction between neighbors in this sense in both dimensions, and competition. And you can see you have swarm behavior. The synapses, the connections talk to each other and prefer coherent structures. The individuals adapt to the swarm, and the swarm is constituted by individuals, like a swarm behavior, till you get a nice organic mapping. That's been well described by equations, and I'm waiting for you to understand that. I just want to show that there are equations. So my conclusion is that the neural code of the brain has the form of structured nets. The origin of almost all structural information, 99.9999% of the structure of the brain comes from this mechanism of network self-organization. Comprehension is based on homeomorphic mapping between schemas and instances, and the guidance of behavior is in terms of mapping of abstract behavioral schemas to actual situations. Thank you.